Hey guys, welcome back. This is going to be day 6 of our IC&D 2 course, and today we're going to break into the topic of wide area networks, or WAN. A lot of the technologies that we're looking at here are beginning to go away. Some companies have got serial connections or T1s out to the internet. They're not totally gone, but they're not really preferable anymore. We'd prefer to get an Ethernet connection that's going to take us to 100 meg or gigabit or even or 10 gigabit fiber. And then that's going to take us up to the service provider. But in areas where that's not possible, we've got to use WAN connectivity, our classic WAN. And this is things like T1s and frame relay and DSL, possibly cable modem. What makes it a WAN technology for me is I'd say anything that's Ethernet based would be a LAN technology, even though we're going far with it. But a lot of times you can actually get Ethernet all the way to and through your provider. And then in scenarios where you can't, that's where we see other technologies in use, such as coax with cable modems, DSL for digital subscriber lines. You've got different versions of that, your T1, you've even got 4G cellular. So a lot of different technologies out there that are available. We'll go ahead and dissect what some of them are today. So let's jump into the WAN section. So the WAN is that area that we don't own, the wires that go through dirt that is not ours. Depending on where you're geographically located, the city that you're in is going to determine what they call the last mile. And that's the connectivity between your company and then your service provider. In certain geographic regions, you're going to be able to get fiber to the premises. In others, they may have coax. And as a worst case scenario, you're going to have just classic telco. Telco could provide DSL, and then your telephone company can also provide things like T1 or T3 connectivity. That's to get you to the service provider. Once you hit the edge of the service provider network, good chance that this is all going to be fiber and that it's all going to be Ethernet. So the WAN technologies that we talk about, a lot of people might assume that it's going to be like if you connect to something via frame relay, it would be frame relay from one edge to the other of the service provider network. And that's not really the case. A lot of times what we're looking at is the last mile technologies, and then everything within the provider network is probably going to be high-speed fiber. So looking at internet versus WAN, WAN is going to be a dedicated connection. It's going to be expensive. It's going to come with a service level agreement, and it's going to take a long time to be provisioned. I hope not, but there's a good chance of that. Your internet connection is not dedicated. Typically, it's going to be shared, even just shared with other people that are using the internet. There's shared resources all along the way with no SLA. There's no agreement in place, or there's no guarantee that says you're going to have a certain level of access. Fortunately, this is inexpensive. I guess I should put maybe $4 signs like Yelp would do over on WAN. Internet access is cheap, and it can be provisioned very quickly. So if we need to connect two devices together, maybe a mobile worker and the main office, we could just do an IPsec VPN across the internet. It's quick, it's cheap, it's easy, but again, there's no SLA. If you're running a shop that's 24/7, 365, and you absolutely cannot tolerate downtime, and you need a specific level of service, and it needs to be guaranteed, this is where I could get a dedicated WAN circuit from a service provider, and I could connect the two offices together. Another way to look at a dedicated WAN circuit is as though you're going to the service provider, maybe your service provider is Verizon, and you say, I have an office in Atlanta, and I have an office in Miami, and I want to connect these two offices together as part of the network. This can be done without ever touching the internet. So you could consider a dedicated connection to be more secure. You just tell Verizon, we want to build this connection. We pop a router at each end, and we could still do a VPN across the service provider's network from one point to another. We could encrypt everything so that even if the service provider is compromised, or if the service provider is snooping, they're not going to see anything communicating between the two offices. How are we doing so far? Any questions at all? All right, lots of thumbs up. Everybody's doing good. Good deal. So looking at WAN devices, what connects us to the WAN? Routers, not switches. And while switches and routers are both capable of layer 3 forwarding, it's routers that are capable of using a serial interface to connect to a CSU DSU, which is kind of like a modem, but it's a commercial grade modem. It's a modem for T1 lines. So you'll have a T1 circuit perhaps, or fractional T1 on one side, and then you'd have a serial connection on the other side. And the serial connection would come into your router. So if you want to take a look at that, let's pop over here and use Google Images real quick. Talked about this a bit in ICND1. Same type of stuff. If we were to look at a router, we could say Cisco WAN interface card. And when we do that, let's go to Images. This is what a Cisco WIC might look like. This is 2 serial ports on one WAN interface card, and it uses a high density serial connection, and that serial connection would go out and would connect to a DSU CSU. So for example, this is what that would look like with the cable being plugged into it, and you could do a back-to-back serial connection. That's okay in the lab if you want to simulate a wide area network, but you'd never really do that in production. You would just run Ethernet from one point to another. Let's open this one up again. Here you can see a WAN cable, and this is a high density connection on one side and the legacy style connection on the other. What that would actually go to, and here's an example of an older 1751 router, and you can see this has got the older style serial connection. You'd have Ethernet come into the router and then serial go out, and the serial connection talks to your DSU CSU. So Adtran is one of the companies that makes DSU CSUs. The last one that I worked on that was external was an Adtran. So it looks something like this, and you say, man, that thing looks like it's from the past. 1980, your 286 Packard Bell came back to visit. But this would be an external DSU CSU. So what happens with this, if we looked at the back side of it here, you'd have a serial connection, and this is an older style V35 serial connection, really, really old. Serial connection comes in one side, and then where it says network here, this would actually be an RJ45 connection, like a typical Cat5e cable might have, and it's going to go from this network connection to a smart jack. So you go from a router through a serial interface into this. And then we come back out of this on the network side, and that's what's going to connect out to your service provider. It's going to plug into a smart jack. So if I just say Verizon smart jack, and I think any smart jack is basically going to look like this, in your telco closet, you're going to have some plywood probably screwed into the wall, and then screwed into that plywood, you've got a smart jack. What this does is it takes the wire that's coming in off the street, and it gives the service provider an endpoint to do all their testing and their signaling. They can control this. And then what comes out of this is that RJ45 connection that goes into that Adtran device. And Adtran is just a vendor, just like Cisco. It could really be any brand of DSU CSU, but that's historically how it's worked. So just to show you a quick review of that, you've got Ethernet on one side of the router, you've got serial connection on the other. So the router would need a serial interface. The DSU CSU has got a network cable, and this could just be a traditional copper pair. I've used, you could just use a network jack for this, a network cable. But what's going on here is you've got a copper Ethernet connection from the CSU DSU to the smart jack in the wall. The smart jack in the wall is what gets you out to the street. The wires, if you followed them, they would take you to a central office, which is everybody's got them in their neighborhoods or communities. It's just the brick building. Mine says Verizon on the outside of it. There's no windows. There's a high fence, and there's a couple vans parked in the parking lot. That's what the CO is. So from the CO to the smart jack is the service provider's job to take care of. This copper that's buried in the dirt is their responsibility. From the smart jack to the DSU CSU is what we would typically call the point of demarcation. Everything on the right side of this is up to you. We go from the CSU DSU through a serial cable to your router, and then the router enters your network with regular Ethernet. Any questions? This is pretty old. If this isn't what you have, you're not missing out on much. Your service provider might just give you a managed router, and they would take, like, my service provider brings fiber into the building, and then they have what's called an ONT, which it brings an optical from the street, and it just puts out Cat5 on the other side. I take that Cat5e, I put it into my ASA, and I'm done. My internal network is right here. All right, so looking at the various devices, if your provider gives you a modem, like a DSL modem, this is technically a router in the sense of it's bringing in one style connectivity that's WAN connectivity over here and LAN over here. Being a router is not so much about routing. It's really about media translation, bringing in some style of technology that goes long distance and dropping it over here to what we use for shorter distance inside the LAN. An optical converter is what I've got for Fios. They bring fiber down the street and into your house. And then at the, in your house, you've got a box mounted to the wall, and it's just an Ethernet handoff. And now here's the customer device, which in my case is an ASA. When looking at serial connectivity, this is what they're going to probably ask you about on the CCNA exam. They're going to target your knowledge of this. What we do is we connect our router to the CSU DSU. A serial cable, if you looked at it, it has two ends that are marked, DTE and DCE. So let's take a look at those real quick. There we go. So there's a close-up of what it may look like. And here's another one. And if you can see, it's a little bit blurry. But in the actual housing for this connector, in the rubber housing, it says DCE on one side, and it says DTE on the other side. So there's a specific way that this cable is supposed to be set up. The DCE side, and you can remember this, it provides the clocking, which if you can remember C in clocking, this side synchronizes with the other side, but it transmits a signal that's used for synchronization. So in a lab environment, you might set up your routers like this. So this would be called a back-to-back serial connection. This wouldn't do anything for you in real life, because if you had two routers that were that close together, just use Ethernet, it goes faster. But this could simulate, in this case, a 56 kilobit per second link. Does that make sense? So this is just a low-speed WAN link between two routers. If you were to do this in a lab, when you plug that cable into this serial interface, if you were to say show controllers serial 1, it would say this side is DCE. So we would go interface serial 1, and we'd have to use a clock rate command. Pretty cryptic configuration. It's not something I've done in production in a very long time, but it is something that they'd want you to know for testing purposes. And that is that the clock rate, and here's a good example of it from somebody else's class, but hey, Google Images found it. Here's two routers back to back with the serial cable. Again, you'd only do this in a lab environment to see how it works. But what they did is they went into the device with the DCE side, and they said interface 000, clock rate 64K. And then that provides the clocking, which will bring the other side up. On the other side, they're using the bandwidth command. The bandwidth command has no effect in performance. And you could probably nitpick that statement. Let me say that the bandwidth command does not control the rate of the interface. The bandwidth command is used to tell the routing protocol the speed of the interface. Does that make sense? I used to think this was for throttling an interface, and it doesn't adjust the rate at which the packets move. It's just for OSPF or EIGRP, when they look at the interface and they want to know how fast it is, we're telling them it's a 64K interface. All right, so if you were to actually wire this up the good old-fashioned way with an external DSU-CSU, put the DCE side on this DSU-CSU, put the DTE side on your router, you should be good to go. Outside of that, what you're probably going to see if you're bringing in like a T1 circuit into a building would be a CSU DSU that actually installs inside of the router, and you wouldn't have a serial interface or a serial cable. You would get a WIC card, which is a WAN interface card, and it would be for T1. So when you look at a Cisco WIC, it could be for a T1, and it looks just like this. And you can notice in the text there that's screen printed on the card, this is a T1 DSU CSU on a card. So we don't have to have that big ugly ADTRAN box with the serial cable running to it. We would just install this card in our router, and then from that port, you would run a wire from here to the smart jack. Now, T1s are pretty old, but they've got WIC cards for DSL. So if you have DSL connectivity, you could get a WIC card so that your Cisco router can speak to the DSL. If you've got cable modem coming into the building, Cisco has a WIC card as well that could terminate a cable connection. Are you guys getting the jive here? And that is that the router can do what the switch can't. The switch handles only Ethernet and MAC addresses. The router can take these special interfaces and he can go out over coax. He can go out over DSL. He can go out over cellular. There are 4G WIC cards. That's one. And it's got antennas on either side. How's that? So if you want to get onto a 4G LTE network like Verizon, I could put one of these WICs into my router, so my backup configuration might go over 4G. Maybe I've got Fios, and that's what I prefer to go over, but if my network connection goes down, if somebody drags a backhoe through my property or they start ripping up the street, that could get broken. So I could have a second interface. And using a WIC, a WAN interface card, this is something that a router can do. It's something that a switch can't do, and it's something that my ASA can't do either. If I wanted to have a backup connection over 4G cellular, I would have to have a router to do it. Why? Because routers can have WAN interface cards. All right, that's probably enough Google images of WICs. You guys get the idea. So looking at the serial cabling, there's different styles. There's the high density that they call a smart serial connection. There's V35, which is the old classic style. You probably won't see a whole lot of these in production. You may, it's not impossible, but you probably won't. Typically when I see these, they're for lab topologies because they used to, I'm not sure if they still test on serial on the CCIE lab, but they used to, so people that were studying for CCIE would set up these WAN environments using serial connections. When you use WAN, you're not using Ethernet typically. When we look at things like frame relay or coax, etc., a lot of times they're running other protocols in place of Ethernet. So for example, if you were to go to Verizon and get a T1 circuit, it might be a frame relay circuit. And what that means is that you're performing what's called packet switching, and you've got frame relay as the technology that's used to basically route your packet or route your circuit from point A to point B. When you look at the encapsulation that gets set here, if this was a serial link, Cisco chooses HDLC by default. HDLC is just the protocol. In other words, we need an envelope for layer 2, and inside of that, we'll have our layer 3, which is of course IP version 4, our layer 4, which will be TCP, and our layer 5 through 7, which might just be remote desktop traffic. Everything looks normal until you get to layer 2. And it's because we don't have Ethernet here, you're just using a different header, which is called HDLC. So that's probably pretty cryptic to most of you. So one of the reasons that I do like to use GNS3, I think this is a great tool as a network guy. Just to goof off and have fun with, this is an excellent tool. I think NetSim is vastly superior for certification training because it's got the lab book and it's structured and it grades your labs and it's written to meet certification objectives. But this is a great way to mess around. what I could do is edit my router here, and I could give it a serial interface. Let's see. Oh, down here under WICs. I can go WIC1T on R6 and hit OK. And then maybe I can drag this up here. And we'll add a WIC over here too. And then what we can do is build a connection between those interfaces. Let's go to here. Add a link, and we want to go from here on serial 0 over to here on serial 0. All right. And then I can shut that off. I can hit play and try to bring this up. Now, what I really like about this, the reason I say this is such a good tool for learning on and just kind of being a network nerd, is I was doing this for many, many, many years, and I never once in my life saw an HDLC frame in Wireshark because I don't have a way to get on an HDLC circuit and see that layer 2 connection. How do I see what this actually looks like? So what we're doing today is we're going to build a connection between R6 and R9 that's a serial link. And if you right-click on it, you can start capturing. And I can say, show me a copy of everything that's going through R6 serial 0. And see how it's got your different encapsulations? So you have to tell it that. We're going to start off with HDLC, but we'll come back and do new captures for like PPP and frame relay as the day goes on. So we'll start here. We say we're going to do HDLC encapsulation. We'll go ahead and we've got our routers started. Let's bring up our console connections. And we'll look at R6 and R9. All right, so starting off on R6, if I do a show IP interface brief, we should see the presence of a serial interface. And this is a little bit crushed. There we go, much better. So serial 0 is administratively down. We can come over here and say conf t interface serial 00 IP address, and this is going to router 9. So I'm going to do 10.10.69.6. And I'll put the mask as a /24, just for the heck of it. There we go. And I'll do no shut. And then we'll go over to router 9, and we'll do the same thing. Show IP interface brief. See, we've got serial 0 there. Conf t int serial 0. And we'll put an IP address on it as well. And IP address 10.10.69. And he's router 9, so I'm going to make him .9. And give him a /24 mask. And no shut. All right. So at this point, if we take a look at our interfaces, we can say do show IP int brief. And our interface is up and up. This is 69.9. And R6, if I move it right next door, do show IP interface brief. We see that he's 10.10.69.6. So I can try to ping 10.10.69.9. Let's do ping. And we went ahead and pinged across that connection. So far, so good. Let's come over to GNS3 again and kick off Wireshark on that link. And what this is going to give us the ability to do is take a look at the encapsulation. And what I'm trying to show you all is that this doesn't look like the Ethernet frames that we've been looking at this whole time. There we go, start Wireshark. So here's my ICMP packets that I sent. And if we look at it, here's normally where we'd have an Ethernet frame. Look how generic this is. It says the address is unicast and protocol is IP. All this does is say I'm carrying unicast traffic, and at the next layer, you're going to find IP data. This protocol is that 0x0800. That's the same value that we saw in Ethernet headers in the protocol field when it was pointing to layer 3. So a very, very simple header. Not a lot going on here. But that's what's being used, not Ethernet. And you go, wait a minute, where's the source address? Where's the destination address? Well, this is a dedicated point-to-point link. Anything that goes in one side is only going to come out the other side. Is everybody all right with that? So if we come into this and we say, show interface 000, we can see that the encapsulation is HDLC. And it's HDLC, show run, it should be show run interface. Oh, I don't do pipe. Show run interface S00. So we didn't set an encapsulation. What I could do is change the encapsulation to PPP. And that's going to break our connection. This isn't something that we've seen yet. But if I do a show interface 000, serial's up, line protocol's up, it's not going to be for very long. So we're trying to send data across. We can see that it's not working anymore. And you see here, the line protocol changed its state to down. Now, we've been doing Cisco together for a couple weeks now, if you were with me in ICND1. And I don't think you've seen an up-down interface yet. This might be a first. Is this a first for anybody? This is a good example of the line protocol being off. See, if you look at protocol, we've got you've got the status of the interface, like administratively down, up or down. This is the layer 1 status. Do we have a wire plugged in? Over here, the protocol, how is the protocol doing? This is basically saying, is layer 2 working? Before it was, because the encapsulation matched. But if I say do show run int 000, we can see this side is set to PPP, and we can verify it here as well. Encap is PPP. And over here on 9, as you could have guessed, the encapsulation is set to HDLC. Because the layer 2 encapsulation doesn't match, you wind up with an interface that's up-down. So if the line protocol is down, if layer 2 is not working, you're never going to send data. You can easily fix that by going into the interface and just saying encapsulation. And you see we've got a couple different options here. We're going to go with PPP. And we should see that interface come back up. And now you might say, okay, HDLC, PPP, who cares? So if that's if that's your attitude, that's okay. Because we've got these different protocols, there's different ways to do things. PPP gives us an advantage. This is the default, and it will work assuming both sides are Cisco. If both sides are not Cisco, we could have some problems. Because this is proprietary. Every vendor's implementation of HDLC is proprietary. So HDLC on HDLC is okay if they're both Cisco. If this other side is a Juniper router, what do? We have to get off of HDLC, and what most people will switch to is PPP. PPP gives us two things. One is vendor interoperability. So that's good. The second thing that it gives us is authentication. See, whenever you take your important data and you send it into the cloud, it's a service provider's job to take that data into the cloud through all of its tons of customers and make it sure that it comes out that exact pair of wires that's going into your office. And if somebody screws that up, all of your data is going to go to someone else's office. So what you can have your routers do is you go, before we even start sending data back and forth, do you know the secret password? In other words, they're just going to do a quick handshake, and they're going to make sure they've got the right password. If they do, the session comes up. If they can't authenticate, well, then it doesn't. So PPP gives you that. We can use this. There's PPP over DSL. There's PPP over cable. As you start to learn more about security, if you ever get into 802.1x, it uses EAP, Extensible Authentication Protocol, And EAP uses PPP. It's basically PPP reborn. It's better and more powerful, but it was derived from PPP. So PPP, this is the most important thing, provides authentication at layer 2 of the OSI model. We've got lots of ways to authenticate, right? I mean, I authenticate to webmail, I authenticate to my bank account online, I authenticate when I log into my computer, but all these things are happening much, much higher. They're at the application layer of the OSI model. What's so cool about PPP is it has the authentication process, and it's not at layer 7, it's all the way down here at layer 2. So vendor interoperability as well as the ability to do authentication. So we'll get into the authentication a little bit more as we continue through this. So when you look at WAN links, I've got 2 offices, they're far apart. That makes it a wide area network. There's 3 main options for how I'm going to connect them. The internet, which is quick and cheap. Dedicated, which is expensive, but I have a dedicated circuit that's mine and only mine. If I bought 100 megabits per second of bandwidth, I will always have 100 megabits that'll be infringed upon by no one. The middle ground is what they call switched. When you hear people talking about frame relay or ISDN, what's happening there is this is a shared topology, and you might get a T1 circuit, and they'll tell you you have 1.544 megabits per second, and we're going to give you an SLA that guarantees you 1 megabit per second. And you go, wait a minute, I thought I had 1.5 meg. And they go, well, it's shared, and we've got it oversubscribed. You know, we've got a 10 meg pipe, and we've got 10 users on it. So you could go up to 1.544, but if everybody's going full speed, you're only going to get about 1 megabit per second. So switched is shared, so your bandwidth could vary, but you're still getting an SLA, and you're just basically sharing the cost. You go, well, we're probably not going to have 100% link utilization all the time, and over 1 meg you actually could very easily. But you figure we don't need all of our bandwidth all the time. Let's go ahead and share it with other people, and we'll get a little bit lower price as far as our recurring billing. So different technologies that could be used. You could go over 4G. You could go over satellite. You could go over fiber. You could have a T3 circuit, which is 45 megabits per second. You could have a T1 circuit, which is only 1.5 meg. We could go over coax with a lot of times your cable company. You could go over telephone lines. Are they missing anything here? Has anyone seen another WAN option? I guess 4G would cover WiMAX as well, but there's power companies. Everybody's heard of power over Ethernet. It's how our phones and cameras work. Well, there's Ethernet over power. You can push Ethernet over a power line. So in some areas, it's not very popular, but your power company could be the one that provides you internet access. So those are just some of the different technologies available. Basically, you have to get from point A to point B. Somebody could do it with satellite dishes, not just satellites that are, 100,000 feet or more above the surface of the Earth. These could be just wireless dishes that are pointed at one another. So you could have towers put up in your parking lot that point across the treetops and connect things. That would be another style of WAN connectivity. All right, so that wraps up WAN as a concept. Now let's talk about serial encapsulation. Serial links are used very often with leased lines because it was the serial link that gets you to that DSU-CSU. When we talk to service providers, a lot of times the speeds that you'll see will be like a T1. You'll see people bundling multiple T1s, like a T2 would be 4 bundled T1s lines for 6 megabits per second. You could have a T3 to hit 45, or you could have a T4 and hit 275 megabits per second. So these are different WAN speeds that are fairly typical. A lot of them are starting to go away, but they've been around for many years. In Europe, they call these E1 through E4, and it doesn't make a lot of sense. While the E1 is faster at 2 megs, an E3 is only 34 megabits per second, and an E4 is 140. So they start off faster, but they miss the top end. Looking at a serial interface, you define the clock rate with the clock rate command. bandwidth with the bandwidth command. Now, in our environment, we didn't have to specify the clock rate. In a real world, if you took two routers and connected them together, you'd need to go to the side that's DCE and say clock rate, and then define whatever speed this link is supposed to work at. You can figure out if you're local to the routers, you can just read the wires and see what the connection is. If you're not local, and this has been like a test question for years, I'm not sure if it's still out there, but you can do a show controllers, and you do your serial interface, serial 0/0, and when you go through this, it'll tell you DCE. And one side would say DCE, the other side would say DTE. All right, looking back at our encapsulation, when we left off, R9 was not doing so hot. Let's see, show IP interface brief, and we see that it's up and up. So show run int 000. I must have fixed my encapsulation, so we're good now. What we can do is look inside and see that the PPP header is just a little bit different. Let's go ahead and close out Wireshark. We'll quit without saving. Pop back into GNS3. Let's stop this capture. And then we'll come back over here one more time and say, let's start capturing. But with serial links, you have to do this. You have to tell it to look for encapsulation PPP. So we'll do that. We'll right-click, start all captures, right-click. That takes a second. Then we can do start Wireshark. And here's PPP messages going across. Let's pop back into our router and just ping router 6, 10.10.69.6. And then we come back over to Wireshark. Here's our pings. And just like before, we've got an ICMP echo request, which is a type 8. The message after is an echo reply. That looks normal. If we look at the IP header, look, it's from 10.10.69.6 going to 10.10.69.9. Looks totally normal. That's the cool thing about the OSI model. If we wanted to go over a serial link, which doesn't use Ethernet, they just switch out this header. So here we've got this funny looking address, we've got a control message, and then we've got this protocol that says we're carrying IP version 4. That's it. So this is the envelope that gets you from point A to point B. It's not anything that you're going to be tested on. And honestly, I've been a network engineer since the 90s, mid-90s, before I even got certified. This is not something I've ever seen in production. Maybe if you work for a carrier and you have access to specialized tools that would look at this, but we never, I was a network engineer for 15 years before I ever saw something here that wasn't an Ethernet frame. So kind of cool that it lets us do that, but moral of the story, really not that hard to set up. We just can set the encapsulation as needed. How are you guys doing? Any questions so far? No questions. All right. Looking at the time, it's about 5:44. Let's go ahead and take a quick break. We'll just stop here for the session, and when we come back, we'll jump into the rest of the slideshow. I'll see you guys back in about 15 minutes.